All right, so just to kind of mention some housekeeping stuff up front. So an Excel assignment is due today, so you should be uploading both kind of your work in Excel, and if you want to type out the answers to the word, more open response where you need a sentence or two, you can upload a Word document as well. So you can submit multiple files. If you want to just upload an Excel with all your Excel work, and then the one that you had to type out a response to, upload a separate Word document for that. You can do that. Okay. But for the Excel part of it, right, I need to see your work in Excel in order to kind of give full credit. So don't just upload a Word document with all the final results, because if it's wrong, I can't give you any partial credit. I don't know where you went wrong. But if I see your Excel file, I can kind of figure out like little mistakes you made and take off small amounts of points for that. Okay. That Connect assignment, because it wasn't showing up, I extended the due date a little bit. So that one's what the due Thursday? No. That says Friday. 14. Yeah. So by the end of the day, Friday, kind of a little bit extra time to work on that. I also put up this chapter for Learn Smart, which I want you to kind of go on and get done before we start class on Wednesday. So notice that due date, the time shows up as 4 o'clock before we start class. Okay. So that's kind of what we have going on this week. I may put up another Excel assignment tomorrow. Just kind of depends. I might hold off until after we meet in class on Wednesday. We'll be doing some more Excel work and kind of getting that up there early. We won't really be able to get too much of work done on it, but I might just get it created so it starts showing up there. So once we start going over things in class on Wednesday that cover the Excel, you'll be able to kind of go on and start working on that. Okay. I apparently need to check my spelling and change the ICR scores there. I'll upload after today. The ICR score is up to date as well once I get back to my office. So you'll be able to see kind of not just the first two we had, but all those since then as well. Okay. Any questions for me before we kind of jump into the slides for this week? Okay. So that Learn Smart will not kind of cover some of the early introductory probability stuff. We'll actually be looking at some more of the difficult kind of issues, kind of the next level. But today we'll introduce the idea. So then when you go on to do that, you'll kind of get some stuff that looks a little bit more difficult, kind of prime you for what we're going to talk about on Wednesday. Okay. So I'll go through a lot of this early stuff pretty quick because a lot of it is just kind of setting us up with thinking about probability. So whenever we ask questions like, what are the chances that something happens, or what's the odds of this investment being profitable, or the likelihood of something occurring, all of those terms are really getting at the same thing. There's something that has several outcomes, right? So if I increase prices, sales could increase, decrease, or stay the same. There's 3 outcomes, and I want to know, well, each of them, I know that some might be more likely than others, right? So each one is going to have a probability associated with it. Just like when we're looking at a variable, right? I might know ahead of time that, for let's say I have the used car data set, right? If I was to choose one observation at random, it's probably more likely that car is black as opposed to bright orange, right? I don't know what color the car is until I actually look at the observation, but I know that different colors are more likely for me to see in that data set. And I would know that from building something like a frequency distribution, right? So we'll eventually kind of talk about how we might use a data set like that to understand probabilities. But for now, we just know we've got all these outcomes and we know some of them are more likely than others. So we're going to define kind of this event of selecting, a random observation as kind of our experiment, right? Experiments, what we'll see, can take a variety of different scenarios, but for the most part, all an experiment is some process that has an uncertain outcome. That's the simplest definition of it. So it's not the same as like we think about, using pipettes and stuff and in science and, these experiments. It can literally be anything. Our only requirement is that this experiment, when we're looking at the results of the experiment, that we're running it exactly the same. So if I'm rolling a dice, right, and it's got 6 sides, right, I know that I could see a 1, 2, 3, 4, 5, or 6, right? Those are the different outcomes I could see. But when I roll that dice, maybe it comes up 2, I record that outcome. Roll it again, comes up 6, I write that down. I just keep doing this over and over and build this data set of all the outcomes I see from rolling this dice. Right? Well, I want to make sure I'm running this experiment the same way. So I want to make sure I roll it kind of the same way every time. If I start then changing it to where I'm just barely dropping over the table to kind of make sure I'm getting the number I want, well, then I'm not really running the same experiment. So we want to make sure we're running the same experiment over and over. And then every possible outcome we could see, we'll call our experimental outcomes. Okay. So maybe imagine a scenario where, a lot of the first examples I'll give, we probably know what the outcomes are. If I'm rolling a six-sided dice, 1 through 6, the experimental outcomes I could see are 1, 2, 3, 4, 5, and 6. If I flip a coin, heads and tails. All right. If I'm drawing, a card from a deck, it's ace through king. Okay. So all my experimental outcomes are all the possible outcomes I could see. Now, let's say I had something that I didn't know, like a card deck, and I didn't know the cards that existed. So I usually use this example, and a couple people sometimes know, but has anyone ever heard of the game Rook, a Rook card deck? No? Anyone? All right, well, it's a great game. It's kind of like euchre, but honestly, a little bit more involved, right? So if I didn't know the cards that existed in a Rook deck, for all I know, it's not numbers. It could just be, I don't know, names of countries. I don't know what the cards look like. So what I might do is start drawing one card at a time. Let's say I didn't know what a regular card deck looked like. I draw a card out, I see a queen. Okay, right, queen down. That was the outcome I saw for the first time I drew the card. Put it back in, shuffle it, draw another card out. Right? Okay, I saw 2. So I know another outcome I could see is 2. And maybe I drew like 5 cards out of this deck. Well, I'm not going to see every possible experimental outcome there because there's more than 5 types of cards, right? So whichever cards I see after I pulled them out of the deck, I'll write them down. That'll be my sample space. I know that those 5 outcomes exist, but if I don't know what a deck of cards has in it, I don't know what all the other possible outcomes are. Maybe it just so happened that when I drew the first 5 cards, all I saw was a number card, right? Maybe I saw a 2, a 6, an 8, and a 10, and a 7. I think I only said 4 numbers there. I don't even know that a queen or a jack or a king exists if all I can see are those 5 draws. So my sample space will sometimes have a smaller number of outcomes than all the possible experimental outcomes. Now, if I run this experiment enough times, eventually my sample space is going to be the same as my experimental outcomes, right? If I draw the card, 1,000 different draws out of a deck of cards, I'm eventually going to see every single possible outcome that, I'll know that, oh, there's different suits, and oh, it doesn't just go 1 through 10. There's a jack, a queen, an ace, right? So that's the idea of my sample space. Then within that sample space or within those experimental outcomes, I might be interested with a specific event. So this event is just going to be what we're interested in finding the probability of. It could be, what's the probability if I draw a card from a deck that I see a jack, a queen, or a king. So it could be multiple outcomes, not just necessarily one outcome. It could be a small subset of the possible outcomes. So visually, right, we're thinking about experimental outcomes or every possible outcome we can see. Our sample space probably contains most of those, but if I didn't take run the experiment enough times, maybe the sample space is a little smaller. And then the event is going to be some specific outcomes I'm interested in, right? A smaller subset. Okay. So if we think about these different examples, I can mention a few, but flipping a coin, our outcomes are going to be heads or tails. We only have 2. But until I flip the coin, I don't know what it's going to be. Right? It's going to be one of those 2, but I don't know which one's going to show up. If I roll a dice here, right? Unless I'm playing Dungeons and Dragons or something, I'm going to see 1 through 6. Right? Choose a card from the deck, ace through king. Say postseason football game, win or loss. Regular season soccer game, win, loss, or tie. Right? So these experiments can take on a variety of different forms. It's just anything that has an uncertain outcome. Okay? Now, most of the examples I used here, the probability of the outcomes are all the same. Right? This is because it's, I'm using these kind of toy examples. As we get through more difficult and difficult examples, some of these outcomes are more likely than others. Maybe for a high quality football team, the probability they win a game is greater than the probability they lose. Right? So we might start to see different probabilities associated with each of these outcomes. Okay. So this idea of probability, how are we going to start writing this out and thinking about it? So it's basically each outcome is going to have a different probability of occurring, right? We're going to write that. Oh, I'll skip that and I'll come back. We're going to write whatever event we're interested in. The probability of that event is P, and then within parentheses, whatever the event is, right? Seeing a 2 come up when we roll a dice, right? Seeing a queen being pulled if we're pulling a card from the deck, right? E is going to be like whatever we're interested in finding. Now that event might have multiple outcomes. So if we have multiple outcomes within the event, we're essentially going to add up the probabilities of those different outcomes. So if I want to know what's the probability if I roll a dice? I see a 1, a 2, or a 3. Well, I would take the probability I see a 1 plus the probability I see a 2 plus the probability I see a 3. I just add up the probabilities of all the outcomes that were within that event. Okay. So we've got this probability of some event we're interested in. What's the lowest this probability could be? Yeah, if something couldn't occur, the probability would be 0. You can't have a negative likelihood of something occurring. It just either has some likelihood of occurring or it can't occur, right? The probability is 0. Okay. The highest it could be is if it was guaranteed, would be a probability of 1. That's not a very interesting example, right? We probably won't deal with problems that look like that because there's not much to do there. Usually we're trying to use these probabilities to understand, well, what we're trying to plan for the future, right? Well, if the probability is 1, it's not that hard to plan for the future. I know it's going to happen. I should make my plan, make my decisions according to that. However, if something, maybe we have an example where the probability of this event occurring is 0.25, the other event is 0.5, another event is 0.1, right? So it's going to be a little bit harder for us to come up with, a response or kind of plan for the future. But once we have these probabilities, we can talk about how we do that. So we know these probabilities have to be somewhere between 0 and 1. Furthermore, we can start to think, if we want to link this up to things we've already done, probabilities are essentially what we were doing with relative frequencies, right? When we took relative frequencies, we were saying, this represents the proportion of the data that has this specific response. Right? Well, here we're saying this experimental outcome happens this proportion of the times we run the experiment, right? So it's synonymous essentially. So our relative frequencies were essentially probabilities. So we said those relative frequencies have to add up to 1. We looked at every single possible outcome we could see for a variable, and we took kind of the relative frequencies. We said they should always add up to 1. So if we take the probabilities associated with every single possible outcome, it's the same idea. So those probabilities of every possible outcome should also add up to 1. Right? So just like with relative frequencies, the sum of our probabilities, if we look across every single possible experimental outcome, those should always add up to 1. Right? It's because we looked at every possible outcome, so it can't be anything else, right? It has to be one of those outcomes. And we said the probability of an event, we just add up the probabilities within it. So if my event is, what's the probability I see a 1, 2, 3, 4, 5, or 6 when I roll this dice? Well, the probability I see one of those numbers is 100% or probability of 1. But really what I was doing there was each number has 1/6 likelihood of occurring, add up 1/6 6 times, and I get 1. And that's kind of the idea behind why some of those probabilities will add up to 1. Okay. So very, very similar to what we're doing with relative frequencies. I'll go over each one of these in depth in just a second. We have 3 different ways that we'll assign probabilities. Right, this isn't that interesting because we're mostly going to be using one of them, pretty much only using one of them. The first one will be the classical method, right? So if I'm if I'm flipping a coin, the 2 likelihoods or the 2 outcomes I could see are 1/2 and 1/2. Yeah, it's been a long day. So the 2 outcomes I could see were heads or tails, right? What's the probability I see a heads? 1/2. What's the probability I see tails? 1/2. Right? Probability of every single outcome, those should add up to 1. Sure enough, they do. Right? This is a new marker because my old one died. So let me see if I can get this to be a little bit more black instead of gray here. I don't know where they ordered these new markers from, but they start out real light colored. So what if I'm rolling a 6-sided dice? The probability that I get a 1 would be what? Probability I see a 2 is, right? All 6 outcomes, that would add up to 1. What was I doing here to get those probabilities? Like, it's kind of intuitive, but ultimately what I was doing was if everything's equally as likely, the probability of each outcome would just be 1 divided by the total number of experimental outcomes. Or kind of like what we were doing with our relative frequencies, right? We'd be kind of thinking about this as like 1 over the possible responses I could see for a variable, right? So if we're using the classical method, the way we assign the probabilities is just kind of 1 over n, or 1 over the number of possible outcomes we could see, right? And I think that one's kind of intuitive. Like, we kind of already are able to think about this one. If I have 100 different numbers in mind, right? And I'm asking you to guess a number between 1 and 100. What's the probability you get it right? Well, there's 100 different numbers. If you can only guess one, 1 over 100, right? 1 over the number of possible outcomes. So that one's pretty easy. If I had, something where I was flipping 2 coins in a row and the order matters, right? The order in which I get heads and tails matters. I have 4 different possible outcomes, right? What's the probability that I get 2 tails in a row here? There's 4 different possible outcomes, so 1/4, right? Or a probability of 0.25. Whoops. Okay. Any questions on that one? One shouldn't be too bad. It's pretty easy, I think, to think about. The empirical method is going to be pretty much the method we use for all of our examples. So I chose something like this, but we're basically going to look at historical data on whatever experiment we're interested in. So maybe I'm interested in, what the favorite cuisine or type of food a Ball State student has, right? So I go out and I survey 60 students, or I survey one of my classes of 60, and I say, okay, look, what's your favorite type of food or cuisine? And I look at the data, and 15 of the students selected Mexican food as their favorite. And so I would say is the probability that if I was to go out on Ball State's campus based off the data I collected, and I ask a student at random what their favorite type of food is, there's a 15 over 60 or 25% chance, or a probability of 0.25 that they respond with Mexican food, right? I don't know what their favorite type of cuisine is, but based off the data, I can assign probabilities to different types, right? So I'm kind of, what I'm doing there is basically what we've already done. I'll go out and I'll look at a data set. I'll look at some variable that I've collected data on. Maybe this is like height, right? I think about, I could go around, get a sample of people, ask them what their height is, record it, and say, okay, based off the responses that I saw, rounded to the nearest integer, if I go out and ask someone, what's the probability that I see them be 7'2", right? Well, I can look at my data, I can figure out I have no responses, or I have 1 response out of a couple hundred, right, from this data set, and so the probability is relatively low, right? But the probability that somebody responds with 5'8", well, I've got 30, 40 people in my data set out of however many I asked, it's a relatively high probability. Right? So I'm just using data to assign the probabilities here. Right? Using past data to assign probabilities for the future. We'll get a little bit of idea of what this looks like when we get to working in Excel, which will probably happen Wednesday. I doubt we'll get there today. And then the last one is kind of subjective method. This is based off some knowledge we have or expertise. We assign the probability. So this one seems kind of hokey, right? You're just assigning probabilities however you want, but it makes sense in some situations. So if you think about a company who's going to choose a CEO, we've got 4 different candidates. I don't want to use the classical method, just assign them all 1/4, probably 1/4 of occurring, because maybe Andy just graduated high school and has only ever had a job, at a fast food restaurant. Well, I doubt his probability of becoming the CEO of this company is very high. It's not 1/4. It's not the same as the other. Maybe the other 3 have already had experiences kind of being the CEO of another company. Whatever it is. One of them came from Harvard or Stanford or something. So classical method doesn't make sense, right? We know these individuals probably have different likelihoods of getting the job. But also it doesn't make sense to use the empirical method, because I can't run this hiring process more than once, right? Once the CEO is hired, we don't just bring the 4 candidates back in and say, actually, we're going to run this again, and we're going to do this 100 times, then use that data to figure out the probability. We can't, that's not realistic, right? So we just have to look at their resumes, look at their experience, and we might know that, one of these candidates, I think Hill I chose here, right? He's already been a successful CEO of other companies, while the other ones have yet to take a position, of similar stature. And so they have, smaller likelihoods of getting that job as that 3rd candidate already has some experience. Right? Now, the company still could go with these other candidates. We just know based off their resumes that different candidates have different probabilities of being hired. Okay? So that would be a situation where we might want to use the subjective method. Now that we have those probabilities, we can start to do some work with them. Right? Like I said, for the most part, we're going to be using the empirical method. Right? If we've got previous data and it makes sense, right? We're running the same experiment again. This is going to be the one that we would most often use. Okay? So with the subjective method, right? Welcome to problem statistics, the class where everything's made up and the numbers don't matter. So it might seem kind of hokey, but there are some situations where it makes sense. If you guys, they did like a reboot of Whose Line Is It Anyways, but if you haven't watched like the originals, you should go back. They got away with a lot more stuff. So, so moving on, now that we kind of know how we're going to assign these probabilities, we need to start doing some work with them. We're going to look at some different ways that we kind of or different situations that we might be interested in finding the probability of. So I'll start out doing this as set theory. It'll look a little bit goofy. Once we actually start talking about probabilities, I think it'll be a little bit easier to connect with, but I think this sets the idea up. So let's say I'm interested in some event A, right? So I'm going to use the dice example because I think it's pretty easy. Think about it this way. I have A, and actually I'll conclude with that with B right now too. All right, so I've got two events, A and B. So the complement of an event is basically every outcome that isn't in whatever event you're in. So A complement, using the superscript C, means every outcome that's not in event A. So A complement is basically not being an A. So what are all the possible outcomes rolling a six-sided dice that would be an A complement? The values in A are just 3, 4, and 5. So A complement would be what? 1, 2, 3. Yeah, just all the different outcomes I could see that were in A. What about B complement? Yeah. 2, 3, and 4 are the only outcomes from the six-sided dice that aren't in event B. So that's the idea of a complement, right? It's just every outcome that's not in whatever event you're trying to find the complement of. I kind of think about, right, it complements each other. When we talk about things that complement each other, it kind of completes it. So this is the idea that if I look at the event and its complement, it's covered every possible outcome, 1 through 6. 1, 2, 3, 4, 5, 6. What if the next one is put the union first? Yeah. First thing we're going to talk about is looking for the union of two events, or the way we often say this is what outcomes are in A or in B, right? The union of these two events. So it can be in either A, or it can be in B, or it could be in both. We don't care, as long as it's in one of them. So if I wanted the union of A and B here, what would those outcomes be? What outcomes are in either A or in B? 5 is one of them, right? 5 is actually in both of them, but I'm not looking for what's in both, right? I'm saying, is the outcome in A or is it in B? It could be in either one. It doesn't have to be in both. It could be, but it could just be an outcome that's in event A or an outcome that's just in event B. So I want the union of these two. What are the outcomes that are going to fit that criteria? 1, 3, 4, 5, 6. Yeah, everything but 2 here. Now, if we have a value that gets repeated, it's still one outcome, right? Rolling the dice and seeing a 5, it still has the same probability of occurring, 1/6. It's just one outcome. It just happens to be the way that the events that we're interested in, it's an outcome that belongs to both events. Okay? Which brings us to the next one, which is this set symbol that looks kind of like a, nope, I wrote that backwards. I was already thinking of an upside down U. The way we read this is A and B, or A intersection B. Okay? So with a union, we have this set symbol that looks like a U. It's actually not a U, it's a set symbol. And it stands for union. That one's, I think, easy to remember, right? So A union B is the same as A or B. A kind of upside down U looking thing is A and B. Sometimes people say it easy to remember, like you got a line going through it, looks like an A, so A and B. I don't know. I think it's easy to remember the union. The other one just means intersection. So a way we'll typically say this is A intersection B, or A and B. Okay? So is it in both of them? Right? What's the outcomes that are in both A and B here? instead of 5, right? The only outcome that's actually in both of them would be 5. Any questions over any of that? Okay, so we won't spend too much time on this one right now. I think later on in the course we'll get there, or not, maybe not till Wednesday. So I'll explain the idea behind it now, but it'll make more sense once we start to calculate and think about the probabilities associated with it. So when we write this vertical line, we call this conditioning on something else. So A given B, so the way that we say this, kind of like there, it's A intersection B, we say A and B. A conditioned on B is the same thing as saying A given B, right? So whatever comes on the right-hand side of that vertical line, we're saying, okay, look, given that event B has already occurred, what are the outcomes left in A you can see? So in this scenario, if I'm telling you, look, I rolled a dice, you can't see it, but I look up there and I go, well, I can tell you that event B occurred. So if you know that event B has occurred, what are the outcomes that are still left in A that you could see? So if I know that event B has occurred, now instead of the entire experimental outcome space of 1 through 6, I know that whatever the dice ended up being, I can see it, you can't, I know it was either 1, 5, or 6. The only one of those outcomes that would still put me in event A would be as if I saw a 5, right? So it kind of limits the number of potential outcomes that we could see. And what it would tell me here is if I know that B has occurred, I know that a 3 or a 4 couldn't have been rolled, right? Because that's not an outcome that's in event B. I always kind of use the example too of just thinking about events. Like if I were to walk outside the building today, what's the probability? We'll put this in terms of probabilities, but what's the probability I fall, right? That's event A. Well, that's not that high, right? I mean, I haven't fallen walking out of the building yet. But if I tell you, okay, given that when you leave the building today, there's going to be freezing rain, what's the probability that you fall? Well, now I know that probability is quite a bit higher, right? So having this additional piece of information that I know is going to be true might influence how likely or unlikely event A is. Right? So that's the idea of what we're going to do with conditional probabilities. Once we do a little more work, we'll kind of come back to this and revisit this with some actual values, and I think it'll make a little more sense. Okay. So we can represent all these things with a Venn diagram. So this rectangle here is going to represent every possible outcome. So every possible outcome we could see for our experiment is in that rectangle. So if I want to think about, to kind of connect my visual to some actual values, the area of that rectangle, if it's every single possible experimental outcome, if I add the probability up of every possible outcome, they always add up to 1. So the area of this rectangle is essentially 1, right? It's the probability of every outcome added up. If I then want to think about just event A, maybe event A only has a couple of experimental outcomes in it, right? So this circle of A represents the probability of all the possible outcomes that are in event A. Okay? So like in this example, it's kind of easy because like event A has 3 outcomes out of the 6. So the probability of A here would just be 0.5, right? So you almost think about it as the area of A here is 0.5. The entire experimental outcome rectangle has an area of 1. The area of B, right? Every outcome in B. The probability we see B, once again, 3 out of the possible 6. So the probability we see event B happen is 0.5. So we kind of draw out, what each one of these areas, kind of what value they have. But the entire space just has an area of 1. If we want to think about the intersection of 2 events, it's basically where circle A overlaps with circle B, right? Or what outcomes do these 2 events have in common, right? So visually, that's where those 2 circles overlap. And then A union B, right? Or A or B, that is it in circle A or is it in circle B? Or it could be in both, right? So one thing to kind of point out here is the union, right, always includes the intersection, right? We can, you can almost break the union down into 3 parts, right? We have like a crescent moon here, we have a crescent moon here, and then we have the intersection in the middle. Okay? So the union is made up of several components. One of those components is the intersection. Okay? That'll come in handy a little bit later on. Any questions on this for keeping it? I don't think that's too bad. So we've got the visual. I'll start using these a little bit, these Venn diagrams. We're also going to look at the information about different events presented to us in the contingency table. Okay? So here I've kept it simple. I've got two events and what their complements are. Right? So I've got event A and its complement, event B and its complement. The first thing we're going to focus on are these top four left cells, all represent intersections. So this cell right here, 0.1, represents the probability of seeing A complement and B, right? Or A complement intersection with B. All these top four cells just represent the intersections of whatever their row and their column headings are. It's not too bad. The totals represent the probabilities of the events themselves. So the probability of A over the total column is 0.6. Probability of A complement over the total column is 0.4. Probability of B go down to the total is 0.5. That's how we read this contingency table. Any questions over that? Because I'm going to start kind of using that fact to do some other things. So I'll point out a couple of things that this contingency table is going to show us. Some of this I might be jumping the gun a little bit and kind of leading us into some future slides, but that's okay. We can put these up here, and sometimes I think it's better to go out of order depending on what I've already said. So if I look at this, right, one thing I'll notice is, well, first of all, give you a nice visual to go along with it. If that's event A complement is just everything outside of A, right? So if I take the probability of A, that's what that circle represents, and I add to that everything outside that circle, or the probability of not being an A complement, what will those add up to? Yeah, it fills out the entire experimental outcome space, so they'll always add up to 1. So notice, excuse me, if I take the probability of A plus the probability of A complement, I should be getting 1. If I take the probability of B plus the probability of B complement, I should also be getting 1. Okay. So the probability of an event and its complement should always add up to 1. Right? You gotta think about it this way. If my event was that when I walk out of the building, I slip and fall, the complement is that I don't slip and fall. Those are the only two possible outcomes. I either slip and fall or I don't. If I do event B, the probability I walk outside and it's freezing rain. Well, it's either, or whatever you call it. Yeah, freezing rain. Well, it's either going to be freezing rain when I walk outside, or it's going to be anything else, right? And the complement of freezing rain outside is any other weather condition, right? So the way that we kind of define the complement, we know that the event and its complement, those probabilities will always add up to 1. Okay. So I'm going to jump the gun a little bit here. Well, no, I think actually this is the next thing I have. Yeah, it is. So we can also reproduce the probability of these events by adding across. Let's say I just left off these total rows and columns. And I just gave you those top four left cells, which I said represent intersections, or right, A and B, A complement and B complement. I can actually add across the rows to reproduce those totals. Notice 0.4 plus 0.2 gives me 0.6. 0.1 plus 0.3 gives me 0.4. 0.2 plus 0.3 gives me 0.5. Right? So why does that work? Right? So I'll try to give you kind of a nice visual as to why we can add across the rows or down the columns to reproduce those totals. So let's say, and having different colors here would be helpful, but I'll try to keep in mind that you just have a pen or pencil. There's another way you can think about it as well. So let's say I've got circle A here. Right? A complement would be, I'll draw these as horizontal lines, but they're red if you can see them. Right? And if you're taking notes, you have two different color pens. Then I have circle B. So where would B complement be? Well, B complement is anything not in circle B, right? So everything just outside of circle B. So I could break this down into two areas. If I think about this part of circle A, right, the part where it intersects with B complement, this like half moon, I would like to shade this in blue. Well, that was where these vertical lines, right, the blue lines, intersected with A. Right? These were all the outcomes that were in A and not in B. Right? So this was the probability of A, and not being in B is the same as B complement. I then had, what are the outcomes that are in circle A and also in B? Well, that was just where those two circles overlapped, right? I'm going to shade in this area right here. So this is the probability of A and B. So actually, I think I did this backwards. I can show it to you another way. So if I add these two together, that completes circle A. I could also think about circle B, right? What did this area represent in circle B? Well, that was just the probability that was in circle B, also not in A, right? The horizontal kind of red lines representing A complement. So that was the probability I was in B and not in A, or A complement. And then what's left in that circle B was just the intercept. So if I add those two things together, it should give me just the probability of B. So notice, probability of A and B complement, probability of A and B complement, plus the probability of being an A and B should just give me the total of probability A. So all that's saying is in that contingency table, take this like blue crescent moon, that's all the outcomes in A and not B. Add to that the outcomes that are in both A and B, right? And that would fill out every single possible outcome in event A. So that's why adding across the rows or down the columns will kind of give you those totals. You don't have to produce a visual like this. Just knowing that fact, I want to give you a little bit of support as to why it works like that. Okay? Any questions on that? And here, if you didn't have colors, right, the vertical lines kind of represented, I believe I was doing B complement, and the horizontal lines represented A complement, or the red. So we can do the same thing with B, right? I just said we can add down the columns to reproduce that total column for event B. Probability of A and B should just be what here? 0.4, right? So those top four left cells all represent intersections for A and B, A complement and B complement. And it's just the intersections, whatever the row and the column headings are. So the probability of A and B is just that 0.4. Right? The probability of A complement and B complement would be that 0.3. Okay? So hopefully, if you're paying a little bit of attention when I was just doing there, I'll give you like 45 seconds to a minute to get your eye clickers out and respond to this one. But this one should be pretty easy. What's the probability of R1 and C1? Right? So give you a little bit of time on this one. It shouldn't be too bad. Right? So some of those cells represent intersections. So which one represents the probability of R1 and C1, or R1 intersection C1? Why not? Let me try restarting this. Let me try restarting it real quick. Let's see if this doesn't. Oh, well, that would help. Hold on. That's not plugged in. Okay. Let's see if we can get it now. All right. Let's try that again. All right, now we can respond with what is the probability of R1. think there's 31 of us. Just a little bit more time. So if you want the probability of R1 and C1 or R1 intersection with C1, which of the following would that be? Just a little more time. All right. Does anybody need more time to respond? If not, I'm going to close it out here. So if you haven't responded, take your best guess. 26 of us here today. Okay, I'm going to close out. So hopefully you see a lot of, okay. See it for a second there. Looks like you guys are kind of listening. Right? I want the probability of R1 and C1, what's that going to be? Yeah, A or 0.4. Right? Those top four cells represent the intersections of the row and column headings. Any questions on anything? Yeah.
So if we had an observation that wasn't in the outside.
Yeah.
How would that?
So let's think about what that represents. Everything outside of these circles, notice, is actually, so if I look at these horizontal lines, then I look at the vertical lines, everywhere where those overlap, they don't overlap within the circles at all. So the area outside the circles where those two overlap, so things that aren't in A and are not in B, that actually represents the intersection of the complements of the events, right? Yeah, actually, hold on to the idea for another 5-10 minutes, and I'll come back to that. So one of the things that, as we kind of progress to the next couple topics that we need to point out before we get there, is order doesn't matter when we're talking about unions, right? Saying A or B is the same as saying B or A. Saying A and B is the same as saying is the outcome in B and is it? It doesn't matter which order I say that. Right? So order doesn't matter when it comes to the union and the intersection. Right? Saying someone makes more than $100,000 and is over 6 foot tall is the same as saying someone's over 6 foot tall and makes over $100,000. Doesn't matter which way I say that, it's talking about the same thing. Right? So I don't know, I always like this one, right? When you say it's fine, it's actually fine, relatively small intersection. Already went over the complement rule, got that one out of the way pretty early. This was just me rearranging it a bit. So I still have it over here. Yeah. So the probability of an event and its complement, we said have to add up to 1. The visual made that pretty easy to understand. If I just rearrange it a little bit, the probability of the complement is just 1 minus the probability of the event, or vice versa. The probability of A is just 1 minus its complement. Right? That's just me rearranging this equation. So the next thing we're going to have is what we call the addition rule. Right? So I'll set this up and I'll show you 2 ways to think about this. So if I want the union of 2 events, right? I'm saying, is it in circle A or is it in circle B? Well, if I just add the probability of A to the probability of B, what I've done is taken this area and added it to this area. So in doing that, I double counted every outcome that was in both of them, right? If I take circle A, add to it circle B, I've double counted what's in both, or I've double counted the intersection of those 2 events. So if I've double counted it, I'll just subtract it out once, and then I'll have only counted everything 1 time, right? I've only counted everything in this crescent moon 1 time, everything in this crescent moon 1 time, and then everything in the middle 1 time. So if we want the union of 2 events, we can simply add up the probability of each event and subtract out the thing we double counted, which was the intersection. Okay. Everybody with me on that? I should be. Any questions on that before we keep moving? So how can I do this with the contingency table? Well, I can find the probability of A and B from the totals, and I can find the probability of the intersection from one of those top 4 left cells. So I'm thinking about, I think I have this. There's another way of thinking about this, but I might come back to this after we talk a little bit more about finding the union. So we'll hold off on this slide. So let's say I want the union of A and B. What I could do, right, is take the probability of each event, add them together, and subtract out the intersection. Okay? So I could take the probability of A, 0.6, add to that the probability of B, which is 0.5, and then subtract out the probability of the intersection, which was 0.4. Just a matter of plugging those values in, and I find that the probability of the union there is 0.7. I was just plugging in those values for those three things. I can find all three of them on my contingency table. Any questions on that? That's probably the easiest way to find a union. There's another way to find the union, and I think it's just good to have the discussion. I would suggest finding it this way. It's probably the easiest way and the way that makes the most sense, right? I'm adding up the two areas and subtracting out what I double counted. Right? So another way of finding this union is actually going to be go to wherever the intersection of the two events are, make an L, and then add them up. This is not a technical way to find the union, but it'll always work. And I'll show you, kind of give you an idea about why it'll always work. I'll leave that up here because I do want to come back to that question asked. So if I'm thinking about, I've got event A. Right? I also have event B. I do a similar thing. I can break this up into three areas. Okay? So this area, I'll then have this area, and then I'll have this crescent moon over here. Okay? So the easiest one is, what is the area of where these two events overlap? What does that represent? The probability of A and B. The way we write that is A, and then this upside down kind of U set symbol thing, right? So we've got one of the three components. What does this area represent? So these would be all the outcomes that are in circle A, but outside of circle B. So that represents the intersection of everything that's in A and not in B, or B complement, right? The intersection of everything not in circle B, but still in circle A. And then what would this blue area represent? Let's take a guess at how I would write that. So these are all the outcomes that are in event B, but outside of circle A. So in B and not in A, or in B and A complement. All right, so kind of broken this down into three different categories. Well, now notice to get the whole, right? The union is anything in either circle. So take this area plus this area plus this area. Probability of A and B, right here. Probability of A and B complement, right here. Third thing, probability of B and A complement, right there. We just add those three up, right? So, it's not that making an L is like this magical, kind of solution, but because we have this 2x2 table, it'll always work out that you want to find the union of two events. If you go to the intersection, make an L and add them up, that's basically going to be giving you the three components that you want. And the one that we've left out is the one that we identified over there. What's everything that's not inside each of these circles? We said over there that that was just the intersection of the complements. Right? So our contingency table will always show us what's in circle B, but not in A, what's in circle A, but not in B, what's in both A and B, and then the fourth thing is what's in neither of them, or what's in both of their complements. Questions on that? So that's why, sometimes if you want to think about this addition rule, we could write it out a little bit different, like break it up into the three areas, take circle A, subtract out what's in both of them. So you're just getting that crescent moon. So probability of A minus the intersection, then take what's in circle B, but subtract out what's in both A and B. So circle B minus the intersection. Now you've got these two parts, and then add in the intersection. Things cancel, and you basically end up with the same exact equation. It's just a different way of thinking about it. Okay? So ultimately, to find that union, I think the easiest way to do it, especially visually too, the easiest way to think about it, is you're just adding up the probability of each of these events and subtracting out that intersection because you would have double counted. Questions on this for moving? All right, so I like that. One definition we'll get out of the way today is, I think I might have already kind of used this before, but if two things are mutually exclusive, that means they can't happen at the same time. So if A and B are mutually exclusive events, there's no overlap, right? There's no outcome that can be both in A and in B. So if there's no outcome that's in both A and B, the intersection would just be 0. Doesn't exist, right? So the probability of the intersection being 0 tells you that those two events are mutually exclusive. There's no outcome that's in both of those events. Okay? Well, that makes our addition rule quite a bit easier. If I want to find the union now, if there is no intersection, I have a visual here. Well, then when I take the probability of A plus the probability of B, I've double counted nothing if they're mutually exclusive. And so I don't have to subtract the intersection. I guess I could, but subtracting 0 isn't going to change anything, right? So two events are mutually exclusive. It makes our union calculation of this addition rule a little bit easier, right? Because there just is no intersection. Nothing's getting double counted. In a contingency table, this would show up as a 0, right? Not very interesting. I mean, we're not going to have examples that have zeros in the contingency table because it's, doesn't make for many interesting examples. So there are many interesting questions that we can answer. Okay? So phone and internet access are mutually exclusive events, right? You couldn't use both of them at the same time. Yeah.
Can you go back to the one last page? Why it doesn't the total?
Oh, because I probably a typo. These should both be 0.7, shouldn't they? You're right. Yep. I probably copy and pasted this over from a different one, and when I changed them, I forgot to change that one. To be completely honest. But yeah, those should both be 0.7, right? Because when I add across the rows or down the columns, you should always give me totals. Yep. Good catch. Any other questions on this before you keep moving? That was a pretty easy one. We can combine some things we've already talked about. I said before, we can really break this whole experimental outcome down into the intersections of the complements, or what's outside of circle A and B. And then we broke down those circles into kind of their 3 parts as well. So we had the intersection of A and B, A intersected with B complement, and B intersected with A complement. So we know those 4 components would have to add up to the entire experimental outcome space. But a little bit easier way to think about this is, what is that area? Is everybody okay if I erase this? Everyone's got this. So if I'm looking at the white area on the screen here, that represents what? The probability that I'm in A. So I'm just thinking about this white area, right? I'm in either circle A or I'm in circle B, right? So that is just the union or, right? I'm in A or B, A union B. That's what that white area represents. I'm in either one of those circles. I might be in both, but I'm in at least one of them. Right? The area outside, I've kind of shown you why this is what it is, but it's the intersection of the complements of those two events. Well, if I add those two together, what should those add up to? Yeah, right. That's the entire experimental outcome space. From there, I know I can rewrite the union as just take the probability of each event, add them together, subtract out what I've double counted, which was the intersection of those two events. All right, so I'm just substituting in that addition rule into that equation. All right, ran out of room here. So I know that those 4 components have to add up to 1. And all that really is saying is, right, those 4 components, right, which really here, this was the easier equation for the union. But what I erased before is we said, we could break that down into like these 3 components. Well, then these 3 components, let me see if I have the visual. What was that? There we go. These 3 components plus the intersection of the complements, these will always add up to 1, right? Because you can kind of see those 4 components are this crescent moon, what's in both the circles, and then everything outside. So we know this equation will always hold, but here's another way of thinking about why it holds. Right, if I first just start out thinking, okay, that white area plus that blue area, that's every single possible outcome, right? They have to add up to 1. And then I'll just substitute in that equation that I know will give me the union, and I know these 4 components have to add up to 1 as well. Which really all this is saying is that those 4 values in your contingency table, all those 4 intersections, those should all add up to 1. Okay? So now we can start to think about problems where if I have 3 of these 4 components, it's just a little bit of algebra to solve for the 4th. Now, a lot of people, when they have a problem like this, they start to try to use the visual, which is a great starting point, but unless you write down the formula, it's very easy to make mistakes. Because when I say something like the probability of A is 0.5 here, it's very easy to think about, okay, that white area is 0.5. No. The probability of A is 0.5. A is this entire circle. So it includes the white area, but also this shaded area as well. So sometimes if you just try to look at the numbers and visualize it, it's probably going to lead you to the wrong answer, just because I don't know. For whatever reason, when I talk with students, I realize like that doesn't connect, right? The visual doesn't quite connect with what we're trying to do with this equation. If we have the equation, it's as simple as plugging in what you know, right? So if I wanted the probability of B, the probability of A here is 0.5. I don't know the probability of B. The intersection, I'm subtracting the intersection, which is 0.1. And I'm adding in the intersection of the complements, which is 0.3, and I know those 4 components have to add up to 1. Now it's just a little bit of algebra to solve for the probability of B, right? So 0.5 plus 0.3 minus 0.1 is 0.7. So I'll subtract 0.7, that cancels, subtract 0.7 from this side, and I'm left with the probability of B is equal to 0.3. So all I did there was plug in the 3 components I was given. I know that all 4 of these have to add up to 1. And that's just a little bit of algebra to solve for that 4th one. So I could have first solved for the problem, like rearrange this equation for what I don't know, like rearrange this general equation to solve for the probability of B and then plug my values in. I think that's a little bit trickier. I think plugging your values in and then just doing the algebra to solve for that last thing you don't know is probably the easier way to do it, right? It's always easier to do algebra when you have the actual numbers as opposed to just some generalized kind of function, but formula or kind of notation. But either way, we'll give you that same answer of 0.3. Okay? Questions on that? So I gave you one. That means if there's no questions, you should be able to answer, right? So I'll give you a little bit of time. This one's very similar, right? So we still have this same equation that we know is going to hold. These 4 components are going to be equal to 1. However, now we're looking for the probability of the intersection. We know the probability of A, we know the probability of B, and we know the probability of the intersection of the complements. So I'll give you guys like 2.5 minutes to work on this, kind of talk to the people around you. Should be very similar to the one that we just did. Okay? So give you a little bit of time to work on that. And I'll get out of the way here so you can see what we did on the board. go for about another 15 seconds or so here. So try to kind of wrap up your work. All right. If you haven't got an answer in, take your best guess. I'm gonna close it out here. 26 of us. All right. All right. So I can basically use the exact same formula that I just did. Right? A little bit of a tricky part to this one. So what's the probability of A? 0.3 plus the probability of B minus the thing that I don't know, which is the intersection. Okay. What's the intersection of the complements? 0.5. I know that should equal 1. Okay. So now it's a little bit of algebra. The algebra that's a little bit trickier here is I've got a negative sign out front. Okay. So before I kind of start moving everything over, the easiest way to do this is I add these up. I've got 1.1 minus the probability of the intersection is equal to 1. All right. I can kind of hopefully see when I'm finishing the algebra here, what would the intersection have to be in order for 1.1 to become 1? 0.1. Or I can kind of move this over to this side and subtract 1 from both sides. These cancel, this becomes 0.1, and I'm left with that probability of the intersection is 0.1, right? So no matter how I want to kind of solve that, I can, however I want to think about that. Once I get down to this point, it might be easy for me to visualize it, but I can kind of complete the algebra as well. Okay. Any questions on that one? So here we've got kind of the answer slide here, or we can go through and calculate this way as well. Okay. Questions on that? We'll keep moving. So 15 minutes left. So I've got a pre-class video I'm going to put up on YouTube. So along with the Learn Smart before Wednesday's class, I'm going to expect that you get on and watch that. I don't know if I'll have, I'll probably have like one specific question about the video, but then the first couple examples that we start going over in class on Wednesday will kind of be along the same topics as what I'm going over in that video. So it's a little example about basically how to find these conditional probabilities and use this multiplication rule. Okay, so it'll introduce, I'll introduce the multiplication rule to you now, and that will just be an example that goes through kind of with the contingency table and shows you how to solve that. So the idea of the multiplication rule is that the intersection of any two events is the same as the conditional probability of an event multiplied by the probability of whatever you're conditioning on. So this one isn't as intuitive. So I'll kind of switch over to thinking about, if I rearrange this, just divide each side by the probability of A, then I'll have a formula that tells me that the conditional probability is just the intersection of those two events divided by the probability of whatever I'm conditioning on. I'll try to prove to you why this holds here in just a second, but this is going to be kind of the useful form of our multiplication rule. We could kind of rewrite this, right? If I do A conditioned on B, it's the same thing, right? It's the intersection of the two events. It's just now I'm conditioning on something else, so I have to divide by the probability of B now instead of the probability of A, because I'm conditioning on B occurring. Remember, whatever's on the right-hand side of that line, that's what I'm conditioning on. Okay? So I've got these rules. This multiplication rule, I'll go over kind of more in that, that pre-class video. It'll probably help us be able to answer something like this, right? But I want to try to give you a little bit of insight as to why this is what it is today before you kind of dive into that video. That'll just kind of introduce the next one of how to calculate. So I'm going to use slightly different Venn diagrams than I was before. So I think it helps with the visual a little bit better. So let's say I've got a space that looks something like this. Right? The area of this entire square Lofton space is 1. Let's say I've got some event A, right, and it exactly splits the entire experimental Lofton space in half. So the probability of A here represents, right, half. I don't know if it's perfectly the scale, but it should be half of this rectangle. let's say I then have event B, okay, which is like the entire, once again, it's not drawn to scale. It should be cutting it in half. I can tell now it's a little bit too low. But the idea is these two events should cutting it in half in different directions, right? So the probability of B here is also 0.5. Okay? Just in a different direction. So if I had drawn this a little better to scale, what should the intersection of A and B be here? Well, if it's perfectly cut in half both directions, this would just be like 1/4 down here, right? Or 0.25. Everybody with me up to that point? So if I'm just thinking about the probability of event A, well, that's just 0.5. We would call that the unconditional probability of A. So we think about here, I'm trying to line these colors up. This is just the unconditional probability of A. But what if instead I condition on event B occurring? We would then call this the conditional probability of A. We're still looking for the probability of A. We've just conditioned on this other event occurring now. We know that B has occurred. So if we just use that formula, right, we think about the probability of A and B divided by the probability of what we condition on B, we've got these values, we can plug them in. Let's think about why it works. So once I've conditioned on B, right, I know I'm somewhere in this space down here, right? So it's almost like my experimental outcome space is no longer 1, it's actually only the outcomes that are in B. So I've told you B has occurred. So now the entire experimental outcome space is 0.5. Of that 0.5, how much of that remaining space is still in A? Well, the intersection of A and B, that was just anything down here in this bottom right kind of rectangular square. So of the 0.5 remaining space, 0.25 of it is still in A. So the conditional probability of A is 0.25 out of the remaining space of 0.5, or 0.25 over 0.5 would just be 0.5. So the idea here is, this is kind of a weird scenario where the conditional and unconditional probabilities are actually exactly the same. And it's because if I look at the original space, half of it was A. But once I condition on B, now of the remaining space, well, still half of the remaining space is in A. So this is kind of a unique example. Next class, I don't think we'll probably talk about today. This would actually be our definition of independence, right? So we'll talk about this a little bit more on Wednesday. But something like this, where the conditional probability of A and the unconditional probability are the same thing, we would say that these are independent events. So this is pretty rare. So I'll show you a more realistic or more likely scenario when we're looking at conditional and unconditional probabilities. So now let's say, we'll kind of go back to, yeah, I can do this. So let's say, I'll use an extreme example. So let's say this entire rectangle is event A again, right? We'll use the same thing. The probability of A occurring is 0.5, right? It's half of the entire experimental outcome space. Now let's say we had, how can I really get at this? I'm really good at that. Let's do, we'll use a circle for B. So let's say something like this. Okay? So this represents B. We'll say the probability of B is, I don't know, not drawn to scale, but we'll say it fills up most of these stuff out. So it's about 0.4. Okay? However, the probability of A and B, we can kind of see here, is relatively small. Let's say it's really, really small. It's something like 0.01. So if I'm thinking about the unconditional probability of B, I'm not conditioning on anything. I've got a highest probability of 0.4. However, what if I wanted to find the probability of B given A? Well, I know that should be the probability of the intersection divided by the probability of what I'm conditioning on. So why does this make sense, right? Well, if I tell you that A has occurred, I now just ruled out almost all of the outcomes that were in B, right? Once I've conditioned on event A occurring, it's almost like I'm saying only these outcomes, right? I'm seeing one of these outcomes. I can rule out anything that's outside of A. Well, the problem is once I'm telling you, okay, well, A has occurred, now what's the probability B occurs? Well, of the remaining space, a very small area of it is actually in event B. So my new base is no longer 1, it's actually whatever the probability of A was, which is 0.5. And the only outcomes that are left in event A that are also still in B, right, is going to be this really small overlap of 0.01. So I'm going to get what? 0.02 here is the conditional probability of B. Right? So you can kind of see here, knowing or having the information that A has occurred, threw out all these experimental outcomes as potential outcomes I'm going to see, because I'm telling you A has occurred, right? Given that A has occurred. So now of my remaining space, a much smaller proportion of it is in event B. The space that I ruled out, a much higher proportion of it was in event B. But that doesn't matter anymore because I've now conditioned on this event A occurring. Okay? So you can kind of see how throwing in these conditionals, it changes kind of the makeup of my remaining space, right, relative to the space as a whole, right? When I'm not conditioning on anything, B makes up a much larger proportion of the entire experimental outcome space. But if I'm just looking at the outcomes in event A, event B makes up a very small proportion of those, right? So I can get wildly dramatic conditional and unconditional probabilities of the same event. Okay? So that's kind of the idea behind why this equation works. It's almost like our new denominator is no longer 1. It's whatever outcome we've conditioned on. And I kind of set up a contingency table example and work through and show you how to use a contingency table to solve for these conditional probabilities, right? You can kind of imagine those intersections, those are in our contingency table. Probabilities of just the events themselves, those are also in the contingency table. So that example I showed you, I think is a relevant, kind of interesting example. It kind of walks you through how to do this. We'll pick up on this, do a little bit of work in Excel next class, and then transition to kind of talking about things like Bayes' theorem. Okay? All right. So make sure you turn that Excel assignment in by the end of the day. Otherwise, I'll see you guys on Wednesday.
Regarding the Excel,
Yeah.
every time I put in the sample variance in Excel, like the equation and everything.